In this video, we're going to talk about logarithmic functions. Previously, we talked about exponential functions that would be in the form with the variable in the power. It's like this one. So f of x is equal to 2 to the x. If I replace f of x with y, I get another form of that exponential. It means the same thing. So this is my exponential function, which is set up to give me the answer to 2 to some power. If I want to rewrite this so that it solves for the power instead, then I'm going to create a logarithmic function. So a logarithmic function allows us to solve for the power. The logarithmic function is organized this way. Notice that your base is 2, so we're going to write it as log base 2 of y, which is sort of like the answer on the other side, is equal to x or the power. You'll typically see it with x here because x is going to be your input, and then y gets used generically as the output. So you could also see it this way. Log base, whatever the base might be, I'm going to write it in general, so some base b of x is equal to y. But as you're working this through, let me label all these things. So as you're working this through, b represents the base. Y, or whatever's on the other side of the logarithm, is the power or exponent, and then x is like that answer to the exponential, which we call the argument. Okay, so how does this work? Let's do a couple of examples so that you can see how this gets pieced together. So for example, let's say that we had log base 3 of 9, and I wanted to figure out what this was equal to. Well, I know that this is equal to some power, so my power is on the other side. 3 is my base. So if I rewrite this in exponential form, this says 3 to some power equals 9. And in order to solve this then, I would need the second power. So the logarithm really says 3 to what power equals 9, and that would be 3 to the second power. If we do a couple more examples like this, I think you'll kind of get the feel for it. If we do a log base 5 of 5, this says 5, so that's my base, to what power? So 5 to what power equals 5? So that's the answer to the exponential. Well, that's just the power 1. So my answer is 1. Let's do log base 2 of 8. Well, I know that this is equal to some power such that my base 2 to that power is equal to 8. So we need 3. We can use this to solve exponential equations. So let's say that we had log base 2 of x equals 4, and I wanted to solve for x. I'm going to rewrite this in exponential form. 2 to the 4th is equal to x. Well, 2 to the 4th is 16, and there's my solution. X is equal to 16. We saw the natural base e in the last video. We're going to have the natural logarithm. So there's two special logarithms, which are the only ones that you can type into your calculator. The natural logarithm is log base e, and the notation is ln. So ln just simply means, so if I were to write this, log base e of x, which you'll never see because we have a special notation for that, and that would be ln. So if you were to do the natural log of something, so if we were to do, well, let's just do the natural log of e equals what? Well, my base on this natural log is e. So if I were to rewrite this in exponential form, base to the power, so e to the power is equal to itself. This is a lot like that 5 one that we had a second ago, and my power would be 1. If we did the natural log of 7.8 or something like that, I don't know what that is. I mean, yes, it would be e to some power equals 7.8. But if you take a look at your calculator will do this one. Your calculator will not do a log base 5 or a log base 2, but it will do the natural log. My natural log is here. So if I turn my calculator on, clear what I've got, I'm going to do the natural log of 7.8, and it tells me it's just a little more than 2, so 2.05. 2.05. We can also use logarithms for solving. So, oh wait, one more. The common logarithm. Remember, there was one other logarithm button on your calculator, and that one's the common logarithm, which is log base 10. We call that the common logarithm because our number system is base 10. So log base 10 of x is equal to log x. So if the base is left off, it's assumed to be 10. Okay, so for example, log 100. So this is equal to some power, right? My base, because it's left off, is understood to be 10. So I would say 10 to some power is equal to 100, which has got to be that power 2. But we have the log key in our calculator. I can't put in a base other than 10 or e on my calculator, but I can go ahead and type log of 100. So log 100 equals, and there's my 2. So I have the natural log in my calculator and the common log in our calculator. So you're going to be working on doing some calculations with the logarithms. You're also going to work on solving some equations with logarithms. We already saw some interest problems. So let's go ahead and take a look at an interest problem that has us use a logarithm. Okay, so for example, let's solve for the time in years it takes 5 grams of carbon to, let's see, I don't know, to double to 10 grams if carbon grows continuously. Okay, so my initial value is 5. That would be P. I'm going to use A equals PE to the RT. I'm going to give you the growth rate. Oops, there you go. I'm going to give you the growth rate as well. So the growth rate, so I've got to give that to you. So the growth rate, let's say that it grows, I don't know, I'll say it grows 14% per year. I am just completely, totally making this up. Okay, it grows 14% per year. So P is my, it's my principal, but it's my initial value. A is my final value, that's going to be 10. R I gave to you is going to be 14, and we're solving this one for T. So 10 is equal to 5 e to the r 0.14 t. Well, I start by dividing everything by 5, and I end up with 2 equals e to the 0.14 t. So I'm going to take this one and I'm going to rewrite it as a logarithm. There are 2 ways to rewrite this as a logarithm. This is my natural base e. So if I rewrite this, I'm going to do it with log first, but I'm going to use an ln. So I know that this would be log base e of 2 is equal to my power, which is 0.14 t, which would be the same thing as the natural log of 2 is equal to 0.14 t. Okay, so there's one way to get there. A simpler way to get there, or I think anyway, to think it through, what I have here works great, but another way to think this one through is to take this equation that we had and apply the natural log on both sides. It's an equation, and whatever I do to one side, I can do to the other. So if I apply the natural log on both sides, the natural log and the exponential base e, their bases match, so they turn out to be inverse functions. So I get the natural log of 2 on one side, the natural log and the exponential base e cancel each other out, just like addition and subtraction would, or a cube root and a power 3, they cancel each other out, and down comes the 0.14t. However you get there, you're going to end up with the same value. I'm going to be doing this one in the next example as well. So that means that we've got the natural log of 2 equals 0.14t. If I divide both sides by 0.14, I'm going to come up with my answer. So I'm going to type this into my calculator. The natural log of 2 divided by 0.14, and I end up with t is 4.95 years. So almost 5 years. Let's do another example. So let's do one similar to this one. This one is a carbon-14 example, so it's actually a carbon dating example. So in this next one, let's see, it says the amount of carbon-14. So the amount of carbon-14 after t years, and they're going to go ahead and give us that continuous, this is a decay, but that continuous formula is given by y is equal to y sub 0. Y sub 0 just means initial amount, that'd be like my p, e to the negative 0.0012t. It says a bone contains 23% of its carbon-14. Carbon-14, how old is the bone? Okay, so the bone that we found right now contains 23% of the carbon-14. Initially, the bone had 100% of its carbon-14. Had 100% of its carbon-14. So initially, this p goes there. So initially, this would be my p. It's 100%. Right now, the value or the amount is 23%. So as I put this together, so y equals y sub 0, e to the negative 0.0012t. And if you're thinking back through those other continuous interest formulas, this would be like my A and that would be like my P. So those really mean the same things. So what was my initial percentage? It was 100%. What's my final percentage? It's 23%. I'm just going to express those as whole numbers. And then I have everything else, e to the negative 0.0012t. We're solving this for t. So now it's a very similar question to our last one. I'm going to divide both sides by 100. I end up with 0.23 is equal to e to the negative, those cancel, 0.0012t. I'm going to apply the natural log on both sides. So the natural log of 0.23 is equal to the natural log of e to the negative 0.0012t. These are inverse functions. So I end up with the natural log of 0.23 is equal to negative 0.0012t. And I'm going to divide both sides by negative 0.0012. Divide by negative 0.0012. So I need my calculator to finish this one off. I've got t on the right-hand side, but I need to go ahead and finish it off on the left-hand side. So the natural log of 0.23 divided by negative 0.0012, and make sure you use the negative at the bottom of your calculator keypad next to the enter sign, not your subtraction key. Otherwise you'll get an error, and I hit enter, and I come up with my answer, which is 1224. So t is approximately 1224. 0.7. I'll keep that one. 0.7 years. Okay, and there's our answer.